Okay, this is part 4 of the lecture on general relativity. At the end of part 3, I gave you a nice thorough description of relativistically what is meant by a black hole. Let me now begin part 4 of this lecture with a similar type of geometrical construct, what is called a wormhole. Okay, as of now, we have never seen any wormholes in nature. A wormhole right now exists as nothing more than math. It's a mathematical solution to the Einstein field equation. Remember, however, what I said in part 3 of this lecture? General relativity makes these wild predictions. Initially, nobody believes those predictions, but then we find objects in the universe that can't be explained any other way. Black holes are a prime example of this. So then therefore, when it comes to wormholes, even though we've never seen any wormholes in nature, general relativity predicts the existence of such a geometrical construct, so then therefore we do in fact suspect that they're out there somewhere. Okay, now what is exactly meant by a wormhole? A wormhole is like a four-dimensional tunnel, if you will, through space-time. Here's the basic description of it. Once again, this specifically right now is just a solution to the Einstein field equation. It predicts a geometry that looks like this. Okay, now what I'm initially drawing here is two-dimensional space like so folded upon itself. This two-dimensional space that I drew here, however, well, that's a two-dimensional version of three-dimensional space. So imagine that this piece of paper here, look at the two dimensions of it like so, as representing three-dimensional space, is folded in this manner. And then in between the two sides of the paper, if you will, is the fourth spatial dimension of hyperspace. Essentially, a wormhole, if you will, is a tunnel through this fourth spatial dimension. Kind of think of it as more or less like two black holes that are kind of connected to each other. So for example, there's one opening, if you will, here. The opening, by the way, of a wormhole is referred to as the wormhole mouth. And then here's another, like so, and then we connect the two with a tunnel, like so. This tunnel through hyperspace, this portion of it is referred to as the wormhole's throat. Okay, once again, this is right here, a two-dimensional representation, a two-dimensional version of three-dimensional space. And then this right here is more or less a tunnel, if you will, through hyperspace. Now, there are some fantastic possibilities that could occur with a wormhole. Some of those possibilities are explored, for example, in the film Interstellar. Once again, Interstellar does get some things correct. It does make some mistakes, but one of the things that it does get correct is through a sequence of scenes in the film, they depict what happens, for example, as the characters pass through a wormhole. Okay, as the characters approach the wormhole, they then see the mouth of the wormhole as a three-dimensional sphere, much like the three-dimensional appearance of the event horizon of a black hole that I described in part 3 of this lecture. At any rate, however, some fantastical things could possibly occur with a wormhole. Here's what I mean. Okay, let's say that right here, for example, is a star or something like that. And then right over here, we'll say is another star, like so. And then through normal three-dimensional space, the distance from one star to the other could be vast. It could be tens or thousands of light years. So then therefore, with a starship, it would take you an extremely long time to go from one location to the other. However, the tunnel through hyperspace, the wormhole itself, this distance here may in fact be very small. For example, say just a couple of centimeters. So then therefore, conceivably, what you can do is enter the wormhole through one wormhole mouth. So here's your little ship, for example, like so. And then essentially more or less instantaneously emerge out the other side, like so. And then therefore traverse vast distances in the universe by taking a shortcut, if you will, through hyperspace. This is basically what the characters do in a sequence of scenes in the film Interstellar. Well, the film does get this sequence correct in terms of what could happen. There are a few other fantastical examples, however, of what might be possible with a wormhole. It is just possible to actually turn a wormhole into a time machine to the past. Here's the basic idea as to how it would work. Let's say, for example, that we construct a wormhole here in this room. Now, how we would actually do that, I'll leave that as an exercise to the student. Well, let's say that we do that, and then right here is one wormhole mouth, and then here's another. So then therefore, if you pass through this wormhole mouth, you then tunnel through hyperspace, and you more or less instantaneously emerge out the other side. Now imagine that the two mouths here of this wormhole are twins, like in the twin paradox. And then what you do is you keep one of those wormhole mouths here on the Earth. Think of that as the Earth twin. And then you take the other wormhole mouth and you place it on a starship. And then the starship goes out and it comes back. And then therefore, the rocket twin, if you will, the wormhole mouth that went out and came back, is younger than the Earth twin. So then therefore, if you moved through the wormhole mouth that remained on Earth, where more time elapsed, you would then instantaneously emerge through this wormhole mouth, the rocket twin, where less time elapsed, so then therefore it's younger. This then means that you have traveled back to the past. Notice that there are some restrictions associated with this, however. You can't use a wormhole to actually travel back to the past before a point where you actually built the wormhole itself. So there is a restriction associated with this. This idea of time travel to the past before the construction of a wormhole has actually already been tested. It was tested very famously by Stephen Hawking, the British physicist, back in 2009. I go through in detail exactly how Hawking tested this portion of the theory in general relativity. I do so in my screencast. Make sure that you watch that screencast at this point, perhaps. You can go ahead and pause my lecture here. Okay, now that you've watched that screencast, let's go ahead and apply general relativity to the universe as a whole. The Einstein field equation, when you apply it to the universe as a whole, makes some startling predictions. Number one, it predicts that the universe expands with no center. I go through this in detail in another series of screencasts associated with cosmology that appears later in the curriculum. However, in addition to that, the Einstein field equation mathematically predicts that the universe may be some sort of finite closed geometry. In other words, the universe itself is probably not infinite. Now, how could you possibly get a handle on how the universe itself could be some sort of finite geometry where when we look out into the universe, it looks infinite in every direction? Well, have you ever played an old arcade-style video game called Asteroids? Asteroids dates back to the late 1970s and early 1980s. That video game actually provides a clue for us. I was an expert, by the way, in that video game when I was about 12 or 13 years old. Boy, I really wish that I had all of those quarters back. At any rate, however, if you're not familiar with the game of Asteroids, here's basically what happens in the game. Okay, here's the screen of the game, like so. And then you're in this little spaceship. It's all in terms of vector graphics. After all, this dates back to the late 1970s, so it's quite primitive compared to today's technology. And basically all that you do in the game is you fly around in your little spaceship and you blow up rocks. Believe me, when you were 12 years old back in 1980, this was a big deal. At any rate, however, when you play the game, it's a two-dimensional universe that appears infinite in every direction. In other words, while you're playing the game, you never come to an edge. However, here's what does happen when you play the game. For example, when you do play the game and you go out the top of the screen, what actually happens is that you come in from the bottom like so, and you end up back where you started. This then means that the top and bottom of the screen are connected to each other. So think of this two-dimensional paper right here as the screen of the game. And then the top and bottom of the screen are connected to each other like so. forming a cylinder. But then the same thing happens if you go out, say, the right-hand side of the screen. If you go out the right-hand side of the screen like so, you actually come in from the left like so, and you end up back where you started. So then therefore, the left-hand side and the right-hand side of the screen are connected to each other like so. So if you connect the top and bottom, and you connect then the left and right, can you envision what sort of geometrical object you end up with? No, you do not end up with a sphere. Instead, you end up with a torus. You end up with a donut. So the universe of asteroids is actually a three-dimensional universe, even though while you're in the universe, it appears to be two-dimensional and infinite in extent. You never come to an edge. But the entire game itself actually takes place on the surface of the torus. So the universe of asteroids is three-dimensional, but if you're a character within the universe, you only experience two of those dimensions. General relativity predicts that our universe may be a four-dimensional version of a torus, what is referred to as a hypertorus. Here's the basic idea as to how this would work. So imagine that this right here is three-dimensional space in the universe, like so, this cube. And now if the universe appears to be infinite in extent, in other words, as you travel through the universe, you never come to the edge, but it does have a finite geometry, then conceivably the following could happen. So let's say, for example, that you're located right here, and then you start moving through the universe. If the universe has a finite geometry, given enough time, you will end up back where you started. So for example, this then means that you would say, move out the front of the cube that I've drawn here like so, and then come in from the rear like so, and then end up back where you started. This then means that the front of the cube and the rear of the cube are connected to each other. Imagine traveling to the right on my diagram like so. You then go out the right-hand side of the cube, you then come in from the left like so, and you end up back where you started. Once again, while you're in the universe, it appears to be infinite in extent, but if it is a finite geometry, then this would happen. Therefore, the right-hand side of the cube is connected to the left-hand side of the cube. And then lastly, imagine going out the top of the cube like so, and then you eventually come in from the bottom, like so. This then means that the top of the cube is connected to the bottom of the cube, like so. Can you envision the object that you end up with if you connect the top and bottom, right and left, front and back, like so? Well, if you're having trouble picturing it, you're not alone, and the reason why is because you end up with a four-dimensional object. You end up with what is called a hypertorus. You end up with a four-dimensional donut. Now, how could we possibly verify this? How can we verify that, in fact, we live in a finite four-dimensional universe, some version of a hypertorus? Here's how we could possibly see this. So, for example, once again, I'll use this piece of paper. Let's say that right here is the Earth. Let's say that right here is a galaxy, like so. And then let's say that we look at the galaxy in this direction, like so. And this red line that I drew right here, let's think of this red line as having a distance of 1 billion light years. So then therefore, when you look in this direction like so, and you look at this galaxy, you're looking 1 billion years into the past. Now, if our universe is some four-dimensional version of a torus, then it's conceivable that we could look at an entirely different direction and see the exact same galaxy. So for example, say like so. Along this black line. Now, how can we possibly look along this black line here and see the exact same galaxy? Well, we would be able to if the right and left-hand side of my piece of paper is connected to each other. For example, like this. I'm going to go ahead and tape it to illustrate. Like so. And now follow the black line from the Earth like so, all the way to that galaxy. So if our universe is some sort of finite geometry, then we can look entirely in a different direction along the black line, for example, and see the exact same galaxy. Here's the problem, however. Along the red line, as I said earlier, that may be a distance of 1 billion light years. So then therefore you're looking 1 billion years into the past. But along the black line like so, let's say at that distance there is 10 billion light years. So then therefore you're looking at the exact same galaxy, but 10 billion years in the past. Well, in the intervening time, galaxy evolution occurs over, say, 9 billion years of time. So then therefore, how do you know that you're actually looking at the same galaxy when you look in two different directions? Because when you do, you're looking at two different moments in time. But it is conceivable that if the universe itself is some finite four-dimensional hypertorus of some sort, then to some extent we might be looking at a hall of mirrors when we look out into the universe. We might be looking at multiple images of the same galaxy, but at different moments in time. It's conceivable that we may actually be looking at multiple images of the Milky Way itself at different moments in time if the universe is connected in some manner. We've looked for this extensively over the last couple of decades, and as of yet, we have never seen any evidence of this. The reason why we think that is as follows. The four-dimensional hypertorus is so large that due to the finite speed of light, we can only see a very small portion of the surface of that hypertorus. Think of this as analogous to asteroids. Remember that the game of asteroids takes place on the surface of this three-dimensional torus. So then therefore our three-dimensional universe around us is on the surface of this four-dimensional torus. And due to the finite speed of light and the fact that the torus itself is so huge that when we look in every direction, the surface of that torus appears to be flat. However, general relativity does suggest that the universe has a finite geometry. If it does have a finite geometry, we may be able to see it in the manner that I just described. Okay, this concludes the lectures on general relativity. Today's shirt was enslaved.